Swayam Prabha. Digital India. Educated India.
Welcome everybody. We're going to try to solve for a structure of a molecule using a combination of spectra. So it's a combination spectral problem, and we did one before. We're going to apply the same principles here. We have an NMR, an IR, and a mass spec. And this is typically what you would have in a lab when you have an unknown molecule. Mass spec is typically used to find the molecular formula. The infrared is used mainly to find the functional groups. The NMR is used to find the exact structure, exact skeletal structure or exact structure of isomer. Because there are many possibilities for its given molecular formula, and it will find you the exact structure for a particular isomer. All right, let's start at the very beginning here with the mass. Find the molecular formula using the spectra. The most important piece of information for that would be the M peak and the M+1 peak. So there is a tiny M+1 peak here, and that would be just one above the M. That's why it's M+1 at 87. Let's use that information. So there are two methods. Method 1 is using the formula. And the formula is the relative abundance. So this is your relative abundance here of the percentage of M+1 over the percentage of the M. So this is the only time we use the Y scale. Times 100 over 1.08, because 1.08 is the percentage of carbon-13 in carbon. That gives us the number of carbon atoms in your molecule, assuming you have just, carbons and hydrogens. Let's put the numbers in here. This is really, really tiny. It's about 1%. And this is a little less than 20, like 18%. But on an actual mass spec, it will print out the numbers for you. So there won't be any ambiguity. But I'm just going to put an approximate number, 1 over 18 times 100 over 1.08. And that gives us 5.14 as the number of carbon atoms. You know that's impossible, because carbon is a number of atoms. So therefore, it's about 5 carbons. So if you had 5 carbons and only 5 carbons, that wouldn't really work out, because 5 carbons times 12 AMU per carbon is 60. If you take that, subtract that from 86, that's going to give you 26 AMU, and if that's all hydrogens, you would have a formula C5H26, which would exceed the number of hydrogens you could put on 5 carbons. Therefore, this is incorrect. Well, let's do the second method then. The second method is just putting in the number of carbons for 86, the possibility. So this is going to be M divided by 12 gives us approximate number of carbons, and we can work from that. So that is going to be 86 divided by 12. That's 7.2, which is about 7 carbons. So, well, can we have 7 carbons in here? 7 carbons times 12 AMU would give us a weight just for the carbons of 84. So we cannot have C7H2 is not really possible. We don't have enough hydrogens. So we got to drop it down. Can we do C6? If we did C6, so the weight of 6 carbons would be 72 AMU. And if you subtract from 86, which is the molecular ion peak, you would get 14. So basically, it would be C6H14. Well, that is 2N plus 2. However, you would just get a hexane. Does our IR information corroborate with that? Well, if you just had a hexane, you would see this and some little CH bends over here. That's not really what you see. You see a very sharp peak around 1700. There are no OH peaks. So it's not a carboxylic acid. Let's try a carbonyl. So the infrared tells us we have a CO at about 1700 for the double bond stretch. Let's put that information in. So therefore, we are assuming we are going to have one oxygen. If you have an oxygen, then obviously you cannot have 6 carbons. We'd have to drop this down to 5 carbons. So let's try that out. So our formula M molecular ion weight would be the weight of carbons plus oxygen plus whatever else we may have, and there's no evidence for nitrogens or anything. This is just an overtone peak of this, plus hydrogen weight. So here molecular weight is 86, and let's do this in AMU. A86 AMU is carbon. Well, we know it's not 6. We have an oxygen here. So therefore, if you have an oxygen, according to your infrared, we'll have 1 oxygen. And therefore, we cannot have that many carbons. So let's drop it down to 5 carbons. 5 times 12 AMU plus 1 times 16 AMU plus HM. We don't know what that is. Let's say this is M. Therefore, M is going to be equal to 86 minus 60 plus 16, which is 76. Therefore, that's going to be 10. So we have, according to this, 5 carbons and 10 hydrogens. This is for hydrogens, and 1 oxygen. So that's going to be our formula. So you can see how mass spec and infrared would help us get a molecular formula. What are the possibilities for this? You also have alkyl groups here according to this. So it could be that you have a carbonyl that's flanked by 2 R groups. That's all the information we can get up to this point. R structure. How do you get to the structure of R then? We can do it with mass, or we can do it with NMR, or both, and see if both coincide and give you the same structure for the side chains. 43. 43 was one of our most important numbers. Do you recall what that was? 43 was typically a propyl. So propyl was CH3, CH2, and CH2. So that's 36. And you have 7. So that is going to be 43. This is 43 AMU for that fragment. We do see that as your molecular ion peak, which means you have a lot of that. What else do you have? Well, not really that much. All the others are very minor peaks. Let's look at the NMR and see if that's correct. Let's tabulate the data like we usually do before we proceed. Let's see what all is in here on this NMR, shall we? Let's look at this again and see, tabulate our data. Let's label this peak A, B, C, D, going downhill. A is going to be a triplet at 1 ppm, just put 1.0. B is going to be, again, this is close enough but not exact, is about 1.7, and it's going to be a, let's see, 1, 2, 3, 4, 5, 6 sextet. This is obviously a triplet, just 3 hills on there. This C is going to be just a singlet, a very tall singlet, and that is going to be at 2.3 around, and D is going to be about 2.5. And as you can see, this is also 1, 2, 3, a triplet. Let's look at the hydrogen ratios here. Let's see how many hydrogens are on each of these groups or carbons. This is going to be 3 centimeters, this is going to be 2, this is 3 and 2. That's perfect. 3 centimeters, 2 centimeters, 3 centimeters, and 2 centimeters. So, do we even have to divide the numbers here by the lowest denominator? Look how many hydrogens we have. We have 10 hydrogens. And this is adding up 3 plus 2, 3 plus 2, a total of 10 hydrogens if you divide everything by 1 centimeter. So, we have a ratio 3 to 2 to 3 to 2. 3 would be maybe a CH3, CH2, CH3, CH2. Okay. Now, you might think if it's 3, 2, 3, 2, those are ethyls, but ethyls would give us a triplet quartet. We don't see a quartet, so we know we don't have ethyls, and these are not ethyls. What else could they be? Let's look at triplet, sextet, triplet. How can you have triplet, sextet, triplet? So you ought to have a carbon that has 2 hydrogens. Let's say this sextet here would have 2 hydrogens, and it should have 5 neighbors. How do we know that? We know that n plus 1 is equal to m. In this case, n plus 1 is 3 for a triplet, therefore n is going to be 2. N plus 1 is going to be 6, n is going to be 5. N plus 1 is going to be 1, n is 0. This guy has no neighboring hydrogens. N plus 1 is going to be a triplet, which is 3 multiplicity, and therefore n is 2. So if you take B, let's say, and let's say these are your B hydrogens, then you got to have 5 hydrogens next door. How can you have 5 hydrogens? Well, you can't have more than 3 on a carbon. So let's say you've put 3 here, you can put only 2 here, and that would give you 5 here. So n plus 1 for this, n is going to be 5. Therefore, n plus 1 would be 6, and that's what's giving you the sextet. All right. So we do have a propyl group here according to this. Let's check to see if these are correct. If you have a peak for this, that is going to be split into 2 plus 1, a triplet. So if you take this, n for this neighbors are 2. So therefore 2 plus 1 is 3. You would expect a triplet. And well, you have 2 triplets. Which of these do you think corresponds to this? This triplet is at delta 1 pm, and this one is at 2.5. If you look at the neighbors, those are alkyl groups. There's no electron withdrawing groups right next to it. Therefore, this is in the alkyl group. Primary alkyl would be around 1 ppm. So we know what this corresponds to, and we know what this corresponds to. This is going to be your HA. Well, that leaves us with C. Here's a carbon, and this carbon has no hydrogens, and let's say this is all you have. You would also expect a triplet just like that. So this one would also have N is equal to 2 hydrogens neighboring. So that is going to be N plus 1 is going to be 3. You would see a triplet. And well, there are 2 triplets after all. So these are probably, and we don't know that yet, but let's assume these are HD. But this one is at 2.5 ppm. So what can you conclude about that? We can see because it's in a de-shielded environment, there must be a group here that's electron withdrawing. And if you look at your chart, 2 to 3 could be a benzene or a carbonyl or a triple bond. Well, what do we see here? Carbonyl. And we don't have anything in the 7 to 8 region. And so therefore, let's assume right now that that is what you have over here, a carbonyl. So we got one side worked out. And let's say that's your R. So here is your R. And we can see that that is exactly what you see on your mass spec at 43 AMU. So both these pieces of data corroborate each other, and we know we have a propyl on one side of your carbonyl. What do we have on the other side? As you can see, you need something else to fill the valence. Oh, well, we took care of A, B, and D, so there's only C left, and C is a singlet, no hydrogens. And on that singlet, you have 3 hydrogens. So there's only one possibility for that. You can have a carbon with 3 hydrogens on over here. And does the multiplicity correspond to that? Well, it says no neighboring hydrogens. N is equal to 0. Therefore, N plus 1 is 1. And that means you have a singlet. It's at 2.3 ppm, very close to this, 2.3 ppm. So these are both de-shielded, mainly because they're next to the carbonyl, which is polar and electron withdrawing because of the oxygen. You know you can flip this up and have a positive here. So since you have a delta positive here and a delta negative here, those are going to be pulling those electrons over here. And you are going to be de-shielded because of those. So all 3 pieces of data here, mass spec data, infrared spectra data, and NMR spectra data point to the same structure, which means you have a carbonyl, you have a propyl group on one side, and you have a methyl group on one side. And so that is going to be the structure that corroborates with the data that we get from all 3 spectra. So in summary, if you have a mass spec, you can use that M and M plus 1 data here to find the number of carbon atoms. Now, if you also have an infrared, that can give you the functional groups, so that would tell you information about heteroatoms like oxygens and nitrogens and sulfur and so on. You can then take that information and verify that by using the mass or the molecular ion peak information. The mass spec here has a 43 peak, and that's our base peak, which shows us that propyl group is probably in the molecule. Okay. We don't unfortunately see a 15 here, but we can conclude from this 43 and the infrared carbonyl that we have a structure with a propyl and a carbonyl. If you look at the NMR points to a triplet, sextet, triplet. Whenever you have a triplet, sextet, triplet, we know that these only have one and one possibility, and that is propyl. Both these pieces of information, NMR and the mass spec, base spec, point to a propyl group. What else could you have? If you put all of these together, you're left with 15, and 15 would correspond to the singlet peak here with 3 hydrogens, and that would be a methyl. So we'll have a methyl and we'll have a propyl on either side of this carbonyl. So that is going to be 1, 2, 3, 4, 5, 2 pentanone. That's your structure for the day, 2 pentanone, guys. You can go home now. Talk to you soon, and I will see you later. Bye.